Welcome to video 6.2b, Standing Waves on Strings Calculations. Let's start with a simulation of standing waves. Remember, when we pluck a string with two fixed ends, we can set up a standing wave because of the reflection of the wave as it goes back and forth between the ends. If we notice at this animation right now, we have the fundamental, and the fundamental frequency is showing us half of a wavelength. I want to show the nodes here. So we see that there's just the fundamental node here, so it just has one half a wavelength. Now I can pull this some, and notice as I pull this, I have the first, the fundamental, the second, and the third harmonic here. And you can tell that it's a second because of the two sides, and here it's the third. Notice, however, that the third harmonic is not very strong. The amplitude is not very tall, and it will eventually die out because as it loses energy, it doesn't have the energy for that third harmonic. But the first and second are still going to stay there for a while. Now, if I pluck even harder, notice the string itself doesn't look like a wave front, but within that we have the first three harmonics going. This time the third harmonic has a higher amplitude, so you can see it more, but it's still significantly smaller than the first and the second. Let me change the frequency a little bit, and I'm going to change the tension a bit as well, and let's start that again. Now if I change the tension, you can notice that it changes the amplitude of the waves that we have. And I can change the speed. And now as I change the speed, you can notice that it's almost going too fast for us to see it moving up and down. And now it's really looking like the standing wave that we had talked about previously. I'm going to increase the damping just a little bit, and this will change our third harmonic some more. Okay, so you notice that as I pluck this and time goes on, the second and third harmonics go away until we have just one harmonic. And we can play with the damping here, we can play with the frequency, and we can cause this to wave more. The more damping will cause these waves to disappear more rapidly. You can keep playing with this, you can pluck harder and harder. You can, depending on the settings over here, we can often get up all the way to 6 harmonics where there would be 6 loops of the standing wave. Let's take a look at this as a still picture of the situation. You will notice that the string appears to be in 2 places at once because of the sort of a time-lapse sort of situation. And we know that this is not really true, it's just moving faster than we can see, so it appears to be in 2 places at once. We have a wave machine in class that we will look at this and look at how it appears as well. Notice that the wavelength of the standing wave is dependent on the length of the string and which harmonic we are creating. The fundamental, this first one here, is also called the first harmonic, and then we have the second harmonic, the third harmonic, etc. The harmonics are also called the first and second overtone, depending on what you're referring it to. We can produce these different harmonics by plucking the string different amounts. Remembering the equation we used before, where we had that V is equal to F lambda. Well, if we rearrange that here, we can get this frequency equation where V is equal to lambda of n. So whichever frequency we're looking at, the first, second, or third harmonic, the frequency of that is the speed of the wave over the wavelength of that particular harmonic. Then we plug this equation, the lambda from this equation, into the equation for standing waves, and we end up with a new form of the frequency equation where the frequency of a harmonic is equal to the number of the harmonic times its speed divided by twice the length of the string. The wavelength of the standing wave is equal to twice the length of the string divided by n. And you can see how that works and ends up looking over here when we look at the fundamental, the second and the third harmonic. So really what this tells us is that the frequency of each harmonic is equal to the harmonic number times the fundamental frequency. So if we're trying to find, for example, if this frequency, the fundamental frequency was, say, 100 hertz, and we wanted to find the frequency of the fourth harmonic, that would simply be 400 hertz, because it would be 4 times 100. Let's look at this problem. If the fundamental frequency of a string of length L is 400 hertz, what is the fundamental frequency when the string length is 3/4 L? Well, we can go ahead and do this through the fact that frequency is V over 2L, and our L is the only thing that's changing, but we know that our frequency is 400 when we have a length of L. So if that's the case, then we want to know what is the frequency when our length is no longer L, but is 3/4 L. We can move the 3/4 to the other side, so we end up with 4/3 x is equal to V over 2L. The V over 2L is our frequency, so this is 400 hertz. So then x is 3/4 of 400, which means that the fundamental frequency when we cut the length of the rope from L to 3/4 L is 300 hertz. You can just reason this out as well without having to go through and show all the steps, but I figured I might as well do the equation for you. Let's look at another equation, or another problem rather. If the third harmonic has a frequency of 480 hertz and the fourth harmonic has a frequency of 640 hertz, what is the fifth harmonic's frequency? Well, we know that the frequency of the harmonics, the difference between the frequency of the harmonics, is equal to the fundamental frequency. So this tells us, just subtracting these two numbers, tells us that the fundamental frequency of this particular standing wave is 160 hertz. So that means that the fifth harmonic must have a frequency of 160 times 5, which means that the frequency of the fifth harmonic is 800 hertz. Again, nothing too complicated here. Just showing you that it's the simple relationships that can be found between different harmonics of the standing waves. Let's look at one last problem. If a string of length 0.6 meters is vibrated at 480 hertz, it produces a standing wave with 3 loops. The question is, what is the wavelength of the standing wave? Well, we know that if there's 3 loops, then that means that we have on our wave, we have 3/2 of lambda. So we know that 3/2 lambda is 0.6 meters. So that means that lambda is 0.6 times 2/3. So the wavelength of this particular standing wave is 0.4 meters. Again, nothing too tricky here, but it gives you a basic idea of how to deal with those relationship of standing waves. That's it for the moment. Bye.